Hey, so welcome everyone to the Quantum PC seminar. So I wish you enjoy the summer so far over in Canada. Today we are happy to have Dr. Zachary Vernon as our speaker today. So Dr. Vernon is the Chief Technology Officer for hardware at Xanadu, where he leads a team of over 100 physicists and engineers to build the world's first fault-tolerant photonic quantum computers. So Dr. Vernon holds a PhD degree from University of Toronto, and he has an expertise in integrated photonics for quantum applications. And today, I think he will tell us more about the recent development of Xanadu's fault-tolerant quantum computing and how to scale it up and make it fault-tolerant. Okay, so Dr. Vernon, it's your stage.
Thank you so much for the kind introduction and also for inviting me to be here. Very happy to speak at the seminar series. And indeed, let me dive right in. I should mention I'm on a laptop here. I can't see anyone in the room or anything like that raising hands. So if you did want to interrupt me with a question, I suppose feel free and just make sure you speak verbally and I'll get to it. But of course, it might make sense also to save those questions at the end, and I'll be sure to leave at least 15 minutes at the end for any Q&A. So let me dive right in. First, for those who aren't familiar with Xanadu, which is a company based in Toronto, just a quick reminder of what our mission is. So our mission is to build quantum computers that are useful and available to people everywhere. We are going on 9 years old this year. Headquartered in Toronto, we do have most of our physicists and engineers on sort of all parts of the stack working here in Toronto, where I am. We also have some team distributed throughout the US, Europe, and a couple other places as the need may be. Primarily a venture capital-backed, VC-backed company. We do have some government support as well, of course, and that's gotten us around in total close to 300 million US in funding. And I think now close to 250 people, roughly half, a little more than half of those work on the hardware architecture side, the rest being on software and other algorithm development and, of course, company operations. I'll also mention, I'm the Chief Technology Officer for hardware. So I oversee hardware related and architectural related work on our fault-tolerant quantum computing stack. So I'll be talking mostly about that. I should mention that's not all we do. We have a sizable, especially software and algorithm development effort, teams dedicated to both. Penny Lane being our premier software product, which has really been rising fast as a leader in quantum software development, quantum machine learning, and in general, quantum application development. And we have a lot of partnerships that both make use of Penny Lane as well as other aspects of our algorithm and software development team. So I won't be talking too much about those, but if that's the sort of angle you're coming from, then definitely do maybe do a little further research on your own about the sort of work that we have in the non-hardware space as well. So I mentioned our mission. I'd like to parse that, and this really helps understand kind of where we're coming from on our hardware approach. Parsing our mission a little bit more carefully, if we think of, to build quantum computers that are useful and available to people everywhere, what do we mean by useful and what do we mean by available to people? Useful for us really means we're going after the holy grail in quantum computing hardware. So that's universal quantum computation, not trying to restrict ourselves to any specific, application-specific use case or quantum simulation. The full Monty. We want that to be fault tolerant, and we believe that really the full return on investment for quantum computing can only be realized once we have a full fault tolerant machine. So we're not playing around too much in the era space of, again, sort of limited algorithms for very cases. We are trying to pursue the full fault tolerant scope. And for us and our applications team has taught us that means something like a few hundred, maybe 500 logical qubits with billions of gates. And those gates need to have an error rate on the order of 1 in a billion or so in order to be useful. So that kind of sets the scope for our first systems, our first utility scale systems. That's becoming more popular as certain DARPA programs have picked up, and we've been using it a lot ourselves. Utility scale quantum computation, which means fault tolerant, error corrected, enough logical qubits, meaning hundreds at least, and an error rate suppressed down to levels that make those high value applications within reach. And that's the scale we think we need to be at to build a quantum computer whose value will exceed the cost, which is the benchmark that more people are starting to measure quantum computing roadmaps by. So that's what we mean by useful. Available to people everywhere refers to our cloud deployed model. So quantum computation, especially using photonics, is a center scale proposition. It's not something that will be tabletop or even room scale. We're talking about thousands of racks worth of devices. That's just how it works in photonics. The lucky thing about photonics is that you can do that. You have the ability to interconnect quantum modules much more easily using fiber optics. And that's what we're following in our model to deliver access to these systems, build them, and then deliver access to them over the cloud. And we've done a few examples of that in the more limited application-specific cases for some of our earlier cloud-deployed hardware in the past. So those two requirements put together really translate to the technological needs of scaling, modularity, and networking. So the ability to scale the system to thousands of racks worth of hardware and millions of chips. That, of course, necessitates modularity. You have to be able to split that up into discrete, mass manufacturable modules. You have to be able to design the system against that constraint. And of course, crucially, where quantum computers are concerned, you have to be able to network them in a way that preserves quantum information between those modules, right? A million qubits put together is only useful if there's coherence that can be maintained across all those millions. You can't split that up into non-communicating chunks and expect it to deliver that power at the application layer. So we need scaling, we need modularity and networking. And most of what I'll go through today on the hardware side is going to be really talking about one of our recent milestones that was published earlier this year, referring to our Aurora system, which was really a demonstration of scaling, the scalability, the modularity, and the networkability of our architecture for fault-tolerant quantum computers. Just to imprint this, visually in our minds, we have this sort of aspirational render of what our quantum data center will once look like. I don't take it too literally because I'm not sure that piece of land actually exists in downtown Toronto. It might need to be filled in, but you can see our office will be sitting somewhere sort of north of the CN Tower there. We're downtown. So we're thinking about a data center scale. That really does mean a building scale system, right? Where multiple floors are dedicated to racks and racks of these devices. So most of what I'm going to be speaking about today is on Aurora. This is our latest quantum computer that we've released for internal cloud access. It's really the convergence of all the different subsystem development that we've been doing for the past 8-9 years. Put together into one functioning model prototype of our fault-tolerant architecture. Leading up to that, we've had a number of different milestones that we've sort of poked our heads above the water surface to talk about publicly. Some of them are component level, things like squeeze light sources, integrated photonic devices. There was our X8 system that's over here in 2019, which is our first, and I think the world's first commercially cloud deployed photonic quantum computer. That was a very limited small scale device. Another squeezer demonstration. Then in 2021, we released Borealis, kind of doing things backwards, having Borealis before Aurora, but that's how it went. And that was another cloud deployed machine capable of quantum computational advantage, of quantum supremacy. We deployed that on the Amazon AWS Bracket service for a year. And then most recently is Aurora. Aurora is really putting together a lot of the hardware level and architectural level advancements that we showcased in all of these earlier demonstrations, this time finally converging all of the different subsystem development into one functioning prototype that reflects faithfully our full fault-tolerant architectural blueprint. So I'm going to be talking and unpacking a lot of the hardware that sits inside Aurora and what kind of benchmarks we ran it through. But I won't talk too much about these, but I will on each of the sort of, as I peel through the different layers of the Aurora architecture, I'll mention, and you'll see on some of the slides that I've tied back some of those core functionalities that are embedded in Aurora that were developed and first showcased in these demos. So it really was all sort of leading to one place, that convergent demo. And I'll try to tie that back to some of the earlier demos. And then hopefully there'll be some time at the end to talk about our most recent hardware milestone, which actually was just published last week in Nature as well, which is our demonstration of a GKP qubit with much better quality than was present in Aurora or really ever before. So that's our unique type of qubit, and that's what really unlocks the power of our architecture. And very happy to have that result now publicly discussable. So I've got some work on that at the end of the deck. And then at the end, I'll also finish up by mentioning some of the sort of non-quantum computing work that we're doing still in the hardware space, making available some of the advances in our hardware capabilities around photonic chip packaging, and then also around our photon number resolving detector system, starting to commercialize those efforts just for the sake of their own technology. Just to mention, since it is still fairly recent memory, Borealis, what kind of our last quantum computer on the cloud. This was an optical table scale system, so this is not something that was actually had any photonic integrated circuits on it. It was a fiber-based system, primarily fiber-based, and really what it was showcasing was the fact that we could create these multi-dimensional, time-encoded entangled states of light using pulsed squeezed states and then sample from them. It was this quantum sampling machine. It uses something called Gaussian boson sampling, kind of mirroring the other approaches that have demonstrated quantum computational supremacy before us by Google and by USTC. In China, there have been some other claims since then. This was a system that really was built for that purpose, to demonstrate quantum supremacy with some constraints of programmability. It needed to be photonic. But really, the story behind the story was the demonstration of these very long fiber delay lines, kind of acting as buffer memory for photonic qubits or photonic quantum states of light that were phase sensitive. And the technology that was showcased in Aurora, in Borealis, forgive me, is really what unlocked the ability for Aurora to scale and to network together all its modules using that phase stabilized fiber delay line technology. So that's all I'll talk about for Borealis for now. In terms of how we see in general,
my question is how fiber-based devices realize quantum supremacy?
How did fiber-based device realize quantum supremacy?
Yeah,
I'm not sure I can answer that in a nutshell in the course of a couple minutes. So I'd encourage you to read a paper. But essentially, how this device worked was a series of 3 fiber loops that were attached to switches, and each of these has a different delay line length. And when you inject a continuous stream of pulsed squeeze light, so squeeze states of light that exist in pulses, this allows you to programmably entangle those squeeze states into a 3-dimensional programmably entangled lattice of squeeze states. So a multi-mode Gaussian state over, in this case, 216 modes of squeeze states that have been entangled programmably together. And then after that, we demux them and sample in the photon number basis from every pulse. And that implements Gaussian boson sampling. And Gaussian boson sampling is classically hard to efficiently emulate on a classical computer, even with advanced algorithms. So for a time, until people sort of really started to pick away at it with some of the more advanced spoofing techniques, it was one of the gold standards for demonstrating quantum computational supremacy, albeit at a very niche kind of arcane mathematical benchmark, as opposed to anything useful. So very broadly speaking, what do all these aspects of the technology that we use to build our quantum computer, what do they contribute as a value proposition for photonics, for FTQC? The one everyone likes to talk about is that there's no cooling required. That's a statement that needs some slight qualification, because if you've noticed carefully, our detectors do need cryogenic capabilities, but it's true that no actual computation happens in the cryostat. So we're not doing any gates. There are never any qubits even in the cryostat. There are only pulses of light that are measured for their photon number information, which allows us to select which of the non-cryogenic modes have the qubits that we're looking for. So that makes it a lot easier to engineer, and I think most people are familiar with that. We can use fairly standard silicon processes that are familiar to the photonic nanofabrication industry, used for datacom transceivers and the like, and other types of photonic products. Modularity, networkability, that's really what I'm going to be pitching you by going in through Aurora. The ability to use fiber optics to network these things allows you to modularize much more easily. Faster clock speeds. Photonics has very high bandwidth. In principle, you can go faster than other modalities. Compatibility with telecom, same reason. Less widely appreciated, I would say, is this one, which is the flexibility and error correction. And by that, I'm referring both to the ability to use qubits that have innate error robustness, and that's what a GKP qubit is, as I'll speak a little bit more about. But also, because photonics has that modularity and networkability afforded to it by fiber optic connectivity, you're able to encode lattices of entanglement that are much more connected than you typically would be able to efficiently create in more restricted topologies, either say planar topologies like in superconducting domain, where you're really restricted to that 2D lattice of connectivity, or even for things with much higher connectivity like trapped ions, they have great all-to-all connectivity, but restricted to only a small set of qubits. And then you have a very narrow conduit between different traps to have entanglement shared between them once the interconnects are worked out, which to my understanding, they're not yet. Photonics really doesn't have that. You can knit together whatever lattice you like, and that allows you to access these more advanced error correction codes, in particular quantum LDPC codes, which is a very powerful technique that's really just emerging on the scene that allows you to get far better physical to logical qubit overheads than would traditionally be thought of in using more traditional codes like the surface code. Okay, so how does that all enter into our architecture? This is a cartoon level picture of how it worked, and then I'll demonstrate how this is sort of or I'll talk a bit about how this is imprinted on Aurora. The three main stages for a photonic quantum computer is you have to make the qubits, you have to entangle them, and then you have to be able to do the gates. So no surprises there. The only difference here in compared to, say, non-photonic architectures is this idea of making the qubits. Whereas matter-based approaches like superconducting or trapped ion, neutral atom, what have you, making the qubits is sort of, they're already there, right? You've got ions. You have to initialize the ions and get them in a trap. Superconductors, you've got to get them into the superconducting state. But the qubits physically are kind of already there once you fabricate them. Not so for photonics, right? The qubits live in pulses of light, very special pulses of light that are described by a quantum state that has to be useful for being able to do the rest, entangling them and being able to do gates. So you have to be able to synthesize these qubits. You have to be able to make these pulses of light in these special quantum states. And nature doesn't give us these quantum pulses of light, these quantum states of light that encode qubits very easily. So to prepare the qubits, we have to do something special. And for us, that is essentially very similar to what we did in our X8 system and our Borealis system, in that we need to prepare multi-mode Gaussian states. So it takes some squeeze states, bunch of copies of small sets of squeeze states that have been entangled together using beam splitters and phase shifters, and then sample from them. So actually doing that same sampling problem, that same Gaussian boson sampling problem that was embedded in our X8 system and in our Borealis system, small versions of that, but repeated very, very many times in parallel, allows you to synthesize some of the time in a heralded way the output states, which allow you to then further refine them into GKP qubits, the special state of light that we're after that encodes our qubit in these pulses of light. So we do that in what we call our qubit factory, and this is an array of many copies of these cells, which generate these small entangled multimode Gaussian states and sample from them using our photon number resolving detectors. And then we input those into a refinery, which selects the best such states based on information from that heralding, and multiplexes them and refines them into pairs of qubits, which are entangled. And that's our kind of basic resource state. And then all we have to do is knit that together into a three-dimensional cluster state. And to do that, that three-dimensional cluster state has to exist in time and space. So again, it's another layer of how things are a bit different in photonics, whereas you typically directly act on, perform gates on qubits and matter-based approaches. In photonics, because the photons, the pulses of light, don't want to stick around, you have to do measurement-based quantum computing instead, which is entangling many of these qubits into a spatio-temporal lattice, a universal resource state called a cluster state. And then to perform logic gates, you perform measurements, and those measurements induce the effective gates. So I'm going to walk you through how all that works. This is sort of at the very highest level, and then we can translate that physically into what goes on in Aurora. So we have to make the qubits, we have to entangle them, and we have to do the gates. And really what Aurora was, showing exactly how you do that according to our architecture, not necessarily in a performant way, but in a functional way. So let's start with GKP qubits, and maybe to begin with, what are they? So GKP qubits, they're abstractly a very special state of light, a single mode state of light. So they exist in one mode. They have if you think of them in how you characterize a mode of light, when a mode is quantum mechanically equivalent to a harmonic oscillator. So if you look at the Wigner function picture, they're grid states. So if you look in a P and Q, thinking of them in quadrature space, and look at the Wigner function, you'll have this grid of alternating regions of positive and negative Wigner function. And that grid state, when you take the marginals and look at the wave functions in P and Q, you'll see these nice, well-separated Gaussian peaks, where what we're exhibiting here would be like a zero state. So you've got peaks only in these discrete separated regions that are shaded white, whereas the one state would be in the peaks lying in the gray regions. And so that's your one state, that's your zero state. So 0 and 1, as you see the difference between these two. And you notice that you need to have that grid structure in Q and P, and it has to be well resolved at the wave function level in Q and P. So this is what you're looking for high quality GKP state. This is quite different than the traditional notion of how you encode a qubit in photonic modes. The typical sort of single photon approach that most think of, and most of the pioneering experiments in quantum optics were done. It works on a dual rail configuration, where a logical zero or physical zero corresponds to a qubit in one mode, a single photon in one mode, and vacuum in the other, nothing in the other. And then a one state would be vacuum in the first mode and one photon in the second mode. So you have to have pairs of modes, and the presence or absence, or which which mode the photon is determines whether it's a 0 or 1. GKP qubits are different. There's only one mode, and we're encoding that zero-ness or that oneness in the quantum state of light that exists in that mode, in that waveguide, in that specific transverse mode, in that specific polarization, in that specific temporal shape. We're encoding either this state or this state, 0 or 1. Now, why do we bother doing that? Turns out that GKP qubits are, in a sense, the ideal optimal photonic qubit. Optimal in what sense? Well, for one thing, gates are deterministic. So if you want to entangle or perform a logic gate on a GKP qubit, you can do that using very straightforward Gaussian linear operations, beam splitters, phase shifters, homodine detectors. So they're sort of easy and they're deterministic, unlike single photons, which have the ability to do gates only using photon counting, which means that if you're doing logic, all the computation has to be in principle cryogenic because the detectors themselves are involved. Those photon counting detectors are part and parcel to actually doing a logic gate. And there's an intrinsic non-determinacy associated with that dual rail single photon encoding. So if you want to do a 2-qubit gate, some of the time it simply fails and you can't get around that. So you have to multiplex away from that as well. Not so for GKP qubits. They're deterministic. They use room temperature friendly operations to perform gates, easily accessible without cryogenic detectors. So using homodine detectors, photodiodes. And sort of to top it all off, in a sense, GKP qubits are mini logical qubits in and of themselves because they already have this redundancy packed into this grid structure, right into this multi-peakness. There are robust to small amounts of loss. A little bit of loss on this state acts as effectively as a Gaussian error that can be handled by conventional quantum error correction that gets concatenated with the GKP encoding. Whereas for a single photon, if you have a loss event, the photon is deleted, right? The qubit is deleted, and you deal with the deletion error. So there's already an intrinsic, mild robustness, a second layer of error correction that you apply by virtue of the fact that you've encoded in this more exotic state. Okay, so how do we make them? Well, as I mentioned, we use little Gaussian boson sampling cells. In Aurora, how we implemented this was small, and by small, I mean 2 to 4 mode. In Aurora, it was 2 mode. In general, probably around 3 modes is where we end up as optimal. Photonic circuits that entangled squeeze states using conventional beam splitters and phase shifters. In Aurora, that's what it looked like. We had 2 copies on each of these cells. In this case, 2 squeezers, and they get entangled on this programmable beam splitter. And then one of each of the outputs goes to photon number resolving detector. Now, this is non-deterministic. So in photonics, you're never going to get away from some non-deterministic element. So here, it's just only in the state preparation. And to deal with that, of course, we have to boost it by multiplexing. And I'll talk about how that works in a moment. So Aurora has quite a few of these. If you look under the hood, each of the sort of top row of blades in the rack have these state preparation modules. And if you take off the hood, you see a little chip here, a bunch of fiber optics and other control electronics. So a very discrete modular way of doing this. Aurora has 24 of these, all based on, as I mentioned, silicon nitride platform. In total, 84 squeezers embedded on these 24 sources chips, feeding 36 PNR detectors. And everything, of course, is packaged in fully solid state. Okay, as I mentioned, the non-deterministic aspect of the state preparation of the GKP qubit heralding means you have to do something else. You have to select from multiple trials in parallel what the best qubit or qubit precursor pulses of light are, where they are, on which fibers are they coming out of this top layer of sources. And we do that using what we call the refinery. The refinery's function is to refine the inputs into the best possible entangled pair of qubits that we can get. And that's our basic resource state. In Aurora, that refinery really just implements multiplexing. You can actually do more on the refinery to make better quality states, but in Aurora, we just did multiplexing. The multiplexer works by taking a bunch of parallel inputs and then selecting based on information fed forward in real time from the detectors, from the photon number resolving detectors that are telling you where the best sources are on every clock cycle. The refinery has to implement that switch pattern into this binary tree. And for this, we use thin film lithium niobate picks. That's what it looks like if you crack one of these modules open. And each of them essentially takes 8 inputs and produces the best pair. So a pair of 4-to-1 binary trees selects the best 8 inputs and distills them to 2 outputs, that best entangled bell pair from all the candidate input devices. The PNR detectors are read out in real time, and then an FPGA tells us how to actuate that switch pattern in order to select those best 2, and again, in real time. And that all happens buffered with a little over 1 microsecond of latency. And we can get that down quite a bit. In Aurora, we didn't bother to go too far, but essentially a 250 meter set of 250 meter stabilized fiber delay lines also, which exist as discrete modules, performs that buffering action, just awaiting that information from the cryostat. Okay, so I mentioned we need next a universal resource state called the cluster state. Right now, all we have is a set of pairs of qubits that are entangled spatially, just at the same clock cycle. And now we need to take those pairs of qubits and we need to entangle them into a universal resource state, a cluster state, which looks something like this, where you've got at different time steps, different pairs of qubits that need to be entangled both within their existing time step, their existing clock cycle, but also there has to be entanglement between clock cycles, because these qubits, these photonic states, they're not around for very long, right? We generate them, they flow through the system, propagate through waveguides and fibers, and then they're consumed later. They're absorbed by detectors. So if you want to do successive operations and maintain that a sort of a qubit worth of information, for example, a very basic operation, just to do the identity gate, you have to be able to teleport your quantum information to the next time step without losing it. And that's done by making sure that you have entanglement not only within one spatial layer, at one temporal layer within space, but between successive temporal layers. So the cluster state has to be spatiotemporal. The spatial dimension of the cluster state determines how many qubits you have. The temporal dimension of that cluster state determines how much depth you're going to, what the gate depth that you're able to go to. And of course, we want to be able to go to indefinite numbers of gates. So that has to be some sort of persistently always generating new layers of these qubits and entangling them with the previous set of qubits, as well as the next set of qubits at every clock cycle. So we do this using a set of fiber delay lines again. These ones don't have the job of buffering, rather they have the job of delaying one half of a subset of these bell pairs, so that we have, so when we start a entangled bell pair where each qubit in each pair is at the exact same clock cycle, and what you do is you delay one half of those. And so now you have entanglement between adjacent channels in space and in time. So the characteristic index of each of these qubits in that pair are now offset, one in space, but also one in time. And that gives you that basic resource state, which now gives you entanglement both between spatially adjacent channels, but also temporally adjacent channels. And these stabilized fiber delay lines also exist as discrete, rack mountable modules that have all the servos needed to actuate for phase and polarization, and all the other drifts that you have to worry about, as well as keeping a stable delay line length. And at the end of all that, that allows you to synthesize a lattice that looks like this, where you're kind of flowing through time, and then at each time step, you've got a bunch of these qubits. In our case, 12 physical qubits at every time step, and these are delineated by between the dashed lines. Okay, so in a sense, it sounds interesting, but it's actually, nothing's really happened yet. All we've done is made a quantum state, and there's no interaction with the user yet. There's no implementation of quantum algorithms. There's nothing, no error correction going on. So now we actually have to do quantum computation. As I mentioned, in the measurement-based model, the cluster state-based model of quantum computation, you implement gates using measurements. And in our case, the measurements are homodyne detection events. So you need to be able to measure quadrature. And this occurs using homodyne detectors that are based on ordinary photodiodes. So that's accomplished in Aurora in the QPU subsystem. And the QPU subsystem is, again, no surprise, an array of chips. In our case, there's 5 of these chips, and we call this QPU because this is the place where we actually do the processing, right? This is where the user's gates are implemented. In addition, each QPU cell has just enough beam splitters to entangle those doublets, those entangled bell pairs that are feeding the different QPUs. We have to now stitch that, do a final stitching operation to generate that cluster state where entanglement is shared, not just between isolated pairs, but where those pairs are now entangling different QPU unit cells. So essentially networking together a bunch of these QPUs together, where you're feeding different QPU pairs of chips with one half of an entangled doublet that existed at different time steps and different spatial steps, spatial indices, that allows you to distribute this entanglement across an array of of QPU cells, where you can then do arbitrary computation on the full cluster. So that's what the QPU cells are for. This is what the chip looks like. You've got these, what we call our macronode stitch, our final spatial stitch operation. Imagine, one half of a pair coming into this QPU, the other half of the pair coming into another QPU, exactly like this, but somewhere else on a different clock cycle. Then you can develop entanglement between the modes that are in this chip and on another chip at both the same clock cycle and the previous clock cycle. And then at the end, we have to do measurements. So every single one of the 12 physical qubits terminates on these homodyne detectors, and then we read them out. And the basis choice of that homodyne detection measurements, the local oscillator phase choice, determines for each of these what the measurement is, what the actual logical gate is that we're implementing. And that's what the PIC looks like. That's what a single QPU cell looks like. It's a little silicon photonic chip coupled to a TIA PCB that's reading it out and controlling it. Also existing as a discrete packaged module that sits within the Aurora rack. Right. So one of the most important primitives that a QPU has to accomplish, and this is true not only in our architecture, but I would argue, I think, essentially every architecture for quantum computation, every hardware modality, to do a full set one day of logical, error-corrected, error-suppressed logic gates, to do universal quantum computation fully fault-tolerantly. There are some operations, non-Clifford gates in particular, that require real-time feed-forward of the gates that you're going to implement on the next clock cycle, the next layer of gates, where those gates are determined by, the settings of those gates are determined by the previous clock cycle worth of qubits measurement outcomes. So this is an important primitive in logical quantum computation, no exception for our architecture. And so what we wanted to do in Aurora was show that we can do this on a single clock cycle, so that we could actuate gate settings on the next clock cycle, on say t+1, where the local oscillator settings, the gate settings, are chosen based on information that was only available at the previous time step, time t. Now, you might not need that to be, that's actually probably a stronger constraint than is strictly necessary in some architectures, right? You might be able to put the system in idle mode for a few clock cycles while your digital subsystem, your digital decoder, is crunching the numbers and trying to figure out what next set of corrective actions to take place on your error-corrected qubit. But we wanted to be stricter, and he said, you know what, we want to do this in a single clock cycle, which for us is 1 microsecond, because it's a 1 megahertz optical clock, quantum clock. So we did that. We made sure that our QPU subsystems had the real-time analog digital loop and the digital logic controller available to it that allowed it to make a decision on what next sets of measurements to make, what next set of gates to implement, that had information available to it from the previous clock cycle worth of measurements. And so we ran it through that benchmark and essentially looked at the difference between correlations on a certain set of measurements in a certain quantum circuit, in particular this quantum circuit where we're implementing over here either an X or a Z measurement on this pair of qubits, and that X or Z is determined based on the previous clock cycle's worth of measurements. And that decision can show up as a correlation that exists as a difference between correlations in those next measurement outcomes. And what you look for is a key signature with feed forward versus the difference when you, instead of making that choice conditioned sensibly on the previous clock cycle, you just choose a random basis choice to avoid biasing yourself. And you see that correlation completely disappears. So this is really sort of more of a technological proof, a sanity check benchmark showing that indeed the full chain of operations that one does need for decoders, error correction decoders, fault-tolerant decoders, to make these real-time decisions is indeed present and working as intended. Now, it's not, I wouldn't say it's doing real error correction. The performance in Aurora is not good enough to sort of make that worthwhile. But it is showing that the full chain of analog, digital, quantum to classical, and back to quantum, that loop of information flow is working as intended. And so if you imagine turning up the performance of Aurora to where that error correction cycle actually would do something useful, then all the moving pieces are in place to make that happen. We also ran a more basic benchmark and switched the full system into squeezed state mode. So instead of selecting the best GKP qubit precursors, we just said, send a squeeze state through, and all the way at the end, from the squeezers all the way to the end, we measured the correlations, the vacuum, the quadrature statistics of each of the bell pairs, and showed that we actually still have squeezing persist on all the bell pairs all the way through the system, despite the very high optical losses that were present. So two kind of core benchmarks that we ran on Aurora. If looking back, right, kind of reflecting on what we showed with Aurora, again, it was a mission to demonstrate systems integration, networking, and modularity. So it's not something where we were trying to show, the performance of our chips. There was a lot of loss in particular that made it a challenge, frankly, to come up with benchmarks and demonstrations that were anything to write home about. But we did, and we set some very strict success criteria for ourselves. Among them, we wanted to show the scale of the system. So we had to have a lot of squeezers and a lot of chips, and they all needed to be networked together. We had to have all different subsystems that are involved in our architecture present. So we had to have GBS cells on silicon nitride. We had to have MUX refinery cells on thin film lithium niobate. And we also had to have QPU cells that co-integrated the local oscillator basis choice as well as the homodynamic detection. And that was done actually on a third chip platform, a silicon photonic chip platform. We had to show phase stabilized interconnects, so we did that. And we also said, just to make it a little bit harder, we wanted the system to run for more than 24 hours without any human intervention. And so we passed that benchmark. And of course, there was that single clock cycle feed forward that we needed both for the MUX and the QPU. The internal code name of Aurora was Operation Feel the Burn. That was, I would say, feel the burn associated with scaling, but it turned into the burn of late nights and weekends work for the team. And we pulled it all off in about a year. I should mention that the chips that were used in Aurora, all of them were fabricated on commercially available platforms that had not been customized for our needs. So things where you could sign up, maybe not for an MPW, but for a dedicated run, in some cases, yes, an MPW on a standard process. And as I mentioned, there were actually 3 different distinct fabrication platforms we used. We used Ligentech's silicon nitride platform for the squeeze state chips, the sources. We used Hyperlight's TFLN process for the TFLN MUX chips, and then we used the AIM Photonics silicon photonic process with germanium photodiodes for the and silicon modulators for the QPUs. So this is really doing, I mean, obviously those fabs have done a great job at making their platforms, but nothing that meets the performance demands or was customized specifically for our needs. Since then, right, and that's why Aurora has a lot of loss in it. We didn't go to any special great lengths to drive down losses to extremely low levels. It was really a demonstration of co-integration, systems integration, scaling, modularity, networkability. Since then, we have never really stopped, paying close attention to those losses and how to drive them down. So what I'll talk for the rest of this session here, about some of the efforts that we've been making in driving down those losses by doing the customizations that we need on those fabrication platforms. But it's important to motivate that by knowing exactly what those requirements are. So when we think of the performance limitations that are in Aurora or in general in any of our components right now, the by far most important and arguably the only one standing in our way of going ahead and building a fault-tolerant machine right now is optical loss. And that's present everywhere, at every fiber chip interface, every waveguide, every component. Anywhere the quantum light touches, it experiences loss. And that's the critical imperfection that needs to be managed the most in order to achieve fault tolerance. So in the paper that we published on Aurora, we also very carefully presented a very careful study of what the loss tolerance of the full architecture that would achieve fault tolerance, when we're talking about full depth multiplexing, the entire scaled up system. Aurora is kind of a limited demonstration of that. So if you imagine now extending Aurora, filling in all the missing pieces there and scaling it up to a fault tolerant design, what losses would be needed to actually go below the fault tolerant threshold. And we presented this as a series of surfaces where you're thinking of looking at the loss tolerance in the 3 principal distinct optical paths within our architecture. And you can see by varying and looking at different configurations for the system, mostly around how the qubit factory works, that you develop different surfaces that separate the fault tolerant region from the non-fault tolerant region. And we want to be sort of outside of this surface inside this surface. And that corresponds to the fault tolerant region. And the different surfaces here correspond to choosing different state factories that have different multiplexing depths essentially. And you see there's different configurations you can choose, but more or less you land at around 1%, 1 to 3%. 1 to 2%. You can go as high as almost 5 in some, but of course that trades off all your loss budget in the other 2. So if you can get around 1 to 3% in all the different paths, then you're golden. Then you've got fault tolerant operation, and then you can start scaling the system up, because if you're below the fault tolerant threshold at the physical layer, in our case, as expressed by the amount of optical loss we have, then scaling up drives your errors down. Whereas if you scale up and keep adding qubits before you've reached the fault tolerant threshold, then your error rate goes up. That's what we mean by the fault tolerant threshold. So at Aurora, we had a lot of loss. We had more than 3 dB in sort of the one loss path, and about 13 dB in the longest path that goes all the way to the QPU. Since then, we've made a lot of improvement, as I mentioned, by taking control of customizing, and we built out our own fabrication team that now more or less develops all our own fabrication recipes and fabrication platforms, of course, working a lot on the design as well of the integrated components and the fiber assembly and the packaging. This is a little out of date. We are actually, even further than this now that we're about 6 months past when I made this table. But we've accomplished since those, in that just essentially a year and a half of progress in customization of these platforms and these fabrication processes, got us about a 7x improvement. If you look from where we are now, a little bit beyond this to the requirements that the architecture demands, roughly a 10x required. In fact, it's a little lower. Last time I calculated this, it's more like an 8x. So I'd argue that, in a few short years, we've already made, almost a 10x, and we actually have less than that to go. So it might seem, like a huge challenge to get to 1 to 3% losses in these paths, and it is, but we're actually not that far off, and we've already come down an order of magnitude in a year and a half. If you look back even further where we started, we've actually come down like 2 orders of magnitude in a lot of our components. So, pretty confident that we can reach our ambitious goals in short order to achieve these loss budgets. I should mention that the gap between what we have in component performance and what we need in the architecture is closing not only from progress in the hardware components, but also progress in the architecture. So a lot of this gap, a lot of these requirements are actually getting easier as our architecture team works hard to develop more loss-tolerant optimizations and configurations for how we prepare our qubits and how we operate on them. Coming back to the hardware a little, so how are we closing that gap from the hardware side? Well, as I mentioned, it's essentially by taking the reins when it comes to customizing fabrication platforms and packaging processes, and fiber approaches, and fabrication recipes. So just to highlight a few of these, since we've taken control of fabrication, if you look at kind of our benchmark silicon nitride waveguides, and this is on 300 millimeter wafer platform, we are now below a dB per meter in our multi-mode waveguides. These are 400 nanometer thick, so high confinement for nonlinear optics. Single mode, a little bit higher, and our goal is to get this below 1 dB a meter as well in single mode. Our TFLN optical switch system, so our MZI optical switches on the TFLN platform, we now have that below 30 millidB per switch, which is very low, and still needs to be lower. But again, that's a battle being won in the clean room, right? By optimizing etch recipes, oxides, and the like, very much at the material science level. And this is actually happening within a production facility, so not in a university lab or in any sort of small R&D fab. This is actually already in a production line. Another major challenge for us is co-integrating high quantum efficiency photodiodes into our TFLN stack, and then adding the silicon nitride that we need for edge couplers. We've got some proof of life there with high QE. I'm not going to cite any numbers since we don't have good yield statistics yet on this process, but we're talking about high 90% quantum efficiency photodiodes embedded in monolithically integrated into these chips. And of course, on the sort of basic passives like phase shifters and beam splitters, we're now below the milli-dB level, so we can meaningfully resolve and measure things like a fabrication tolerant directional coupler that has around milli-dB or lower of loss. And that's around where we need to be in terms of the amount of loss that we're adding to the system from design. And this will go down then as we also improve the core waveguiding layer contribution to the loss. Very important is packaging. So in Aurora, all the chips were packaged. They were mostly packaged by us, in some cases by other partners too. But the packaging loss was, obviously a struggle. A lot of that 13 dB comes from the in-coupling and out-coupling, for example, to the different chips. So we've built out our own state-of-the-art ultra-low loss packaging facility using all industrial grade equipment, from wafer dicing, optical grade, all the way through to die bonding, fiber attach using industrial grade manufacturing equipment. And that's gotten us to the level of around a 0.1 dB chip fiber coupling, to specialty fiber a little bit higher when you're talking about arrays. But that's continuously coming down, in large part due to a collaboration, a joint development that we just signed and announced with Corning for custom fiber and custom fiber array development, just to build these fiber arrays exactly meeting the specifications that we need. And then finally, on our detector stack, in particular, the ones that are involved in selecting the GKP qubits, these are our photon number resolving detectors. We've done a lot of optimization on the fabrication recipes, but also on the optical stack. And we're proud to report that we have what we believe is the highest detection efficiency for any photon counting detector of any kind, which is just shy of 3.9, so 99.89. Of course, that's system efficiency. So once you're in the fiber, how many photons do you detect, or what fraction of the light do you detect? So that's not, factoring out or correcting for anything. And this is a true photon number resolving detector. So there's no photon number dependent efficiency. This is just the single parameter detection efficiency equivalent, essentially an equivalent loss that you apply to the state before you detect it. So the lower bound here would be something like 99 point. You saturate this lower bound 99.36%, certainly well above 99% DE. We sped them up a lot, and to transfer this process to, again, large scale production, we've just signed a agreement with Applied Materials to do a transfer to a 300 millimeter process on their pilot line. Those put together, those advancements in our essentially optical loss by tackling things at the fabrication level, have allowed us to generate a much, much better GKP qubit than was ever present in Aurora, or indeed ever present anywhere. So this result was actually just published last week, again in Nature. It was work that happened essentially at the end of last year, beginning of this year, from a new batch of chips that arrived. The first ones that were fully built that expressed some of these, manifested some of these loss improvements in our silicon nitride, as well as improvements in the detection efficiency of those PNR detectors. So this is sort of just like one primitive within the top row of what's in Aurora, but much more performant. And here we did a 4-mode GBS cell. So we entangled together 4 squeeze states using this static, tunable but static interferometer. And then we detect on 3 of the outputs using our photon number resolving detectors. And then we did full homodyne mode tomography on the output heralded. And what we get is this beautiful state with 9 regions of Wigner function negativity, a very nice grid structure, 4 well-resolved peaks. And in fact, you can show that this chip, this same circuit, is generating states that are compatible with fault tolerance, provided you could reduce the loss further. So we don't need to scale up the size of this chip or add more modes or change the structure of these states too much. This device itself, if we could make it even lower loss, then in fact it would be heralding states that would be ready to go for fault tolerant operation. So sort of really, changing the game when it comes to the quality of the qubits. We can now measure things like qubit level metrics on these states and start talking about them rather than talking in terms of quantum optical properties. Okay, so I'm just going to finish up, mention, we've done a lot of work with DARPA lately. We've been selected for the DARPA QBI program, which is all about arguing that the quantum computer we'll build will be justified in its cost by how much value it will generate. We've also been taking some limited side projects, again, in this case for DARPA's Inspired program, where the technological requirements of these programs line up very well with what we're doing anyway for our quantum computing stack. In this case, it's a quantum sensor program to deliver a squeeze state measured and generated on the same chip with a 16 dB of squeezing. And our partners were subcontracted to Raytheon for this. So just kind of giving a picture of some of the side projects that we are taking on. And one of them is this is perhaps of interest to anyone who is doing PIC work, quantum photonic work on integrated photonics. We are now commercializing our packaging services. So we're able to take customer orders in our photonics pilot packaging line to do ultra low loss chip fiber coupling. Again, taking wafers in, or even chips, but could be wafers or chips, and then producing packaged chips out. And what we do is kind of promise you as low as possible added induced loss from the packaging process. So of course we can't go beyond what your chip stack allows intrinsically, but if it is a low loss platform, then we can kind of assure you that we'll have very, very minimal additional loss. And for anyone who's worked in this area, probably experienced the same as us, which is that it's very hard to convince a commercial packaging facility to take the level of care needed to produce an ultra low loss package device, when say your edge coupler might be capable of it, but the packaging process doesn't respect it. It can be very frustrating. So you can reach out to me if you're interested in this, or if you're interested in photon number resolving detector systems. As I mentioned, we are commercializing these. We have sold one system to the Canadian government, and we've got a line of other customers that are also interested in using this. Different versions of this system are available. So again, if it's something you could make use of in your lab, feel free to reach out and send me an email. And with that, I will conclude. Happy to take any questions, and thank you so much for your attention.
Thank you for the wonderful talk. So my first couple of questions online. So the first question, I think they mean that when now Xanadu's technology is getting more mature, so you have GKB state and you have the Aurora. So then can you offer a discount for us to use it cheaper and to try something else ourselves?
Aurora is not publicly available. So it's available for internal access, and we've decided not to do a cloud deployment of Aurora for wider use. If there's a very particular special project that you'd like to use it for, it might be possible, but that'll be heavily filtered by whether it makes sense for both sides. So I would say reach out to me and I can have a look into it. We'd essentially decided not to go through the trouble because frankly, we don't believe there is a ton of application value in these near-term systems, whether they be our Aurora or honestly any of the other commercially available cloud deployed systems that exist in the NISC era. So we're kind of holding off on further large-scale cloud deployments and supporting that until we're closer to fault tolerance.
Okay, great. Yeah, the next question is when you talk about the refinery process for the GKB state, so is that the key to need to the fault tolerance in your architecture?
Sorry, could you repeat that? I didn't quite catch it. When
you talk about the Aurora system, you mentioned a process of the refinery process to make a better GKB state. So the question asked, is that the key to make it the fault tolerant architecture?
Well, it's one of them. I mean, you need certainly good GKP qubits, but that's not the only thing you need, right? You need to be able to operate on them. You need to be able to do logic gates on them. You need to be able to do real-time feed forward and all the decoder operations. So that's kind of the point of Aurora, is putting it all together. It's true that the GKP synthesis is probably the hardest part. It's the part that is costliest too. It requires the largest footprint, and most of the data center will be occupied by hardware that's essentially dedicated to making GKP qubits, but it's not the only thing. Would I say it's the key? Well, it's one of the keys.
Okay, any other question from the audience or online?
Yeah, I have a question actually, if I may.
Yeah, sure, Andrew.
Thanks. Actually, I have like about 2,000 questions, and I have to make a random number generator to pick one. It was an awesome talk. I guess one that came to mind is I don't really understand when you're talking about how the homodyne measurement like leads into your fault tolerant or to your measurement-based quantum computing. From what I understand, like when you're doing a homodyne measurement, you're kind of sampling a probability distribution, and you take a bunch of them and you build up that probability distribution. In your architecture, are you just doing a single homodyne measurement, like a single piece of photocurrent and getting a measurement out of that? And if so, how does that work?
Yeah, that's right. I mean, in a sense, if you think of any quantum measurement, even in conventional qubit circuit model, that's all you're doing, right? You're doing a measurement that samples from a probability distribution. And for our encoding, whether something is a 0 or 1 is equivalent to whether it's in one of the gray bins or the white bins. If you go back to kind of the picture of how that works here. So if you did a measurement here, say, say you're measuring on Q, you'll find a certain probability of it being 1 and a certain probability of being 0. Now, this is meant to be a 1 state, not a perfect one, because there is some probability in the 0 regions. But as it gets better and better, that gets suppressed. And so you'll only get something ever for a sort of ideal GKB qubit in 1. So it is a single shot measurement. It'll give you a 0 or 1 by that binning. But certainly there's a probability of getting something either wrong, or if it's in a superposition state, you could get one or the other based on the corresponding amplitudes.
100%. That makes thank you. That clears it up. Thanks very much.
Yeah, and definitely understand how when we used to homodyne detection in the context of like reconstructing the quadrature statistics to show how much squeezing we have, it seems like it shouldn't be a single shot measurement, but actually it is. It's just another quantum measurement of an observable.
Okay, Rogerio, the next.
Thank you, Zach. That was an amazing talk. So my question is, where does the GKP state live? Does it live in a single fiber? Is a single mode fiber?
Yep. Yeah. So from the first time that a GKP qubit fully refined exists would be in the output waveguide of the refinery, but before it gets entangled into a pair. And then, once it's in that pair, I guess you never have a single standalone GKP qubit because they're always in pairs that are entangled. But if you think at the pair level, they exist, in fiber, and then they get distributed to different QPU cells, which then go back into waveguide.
I see. And what is the rate of production for the GKP state?
So everything operates at a 1 megahertz clock in our architecture. It might go up to, say, a couple megahertz if we improve the PNR speed a bit. But that's essentially the rate. Now, the total rate would be, the number of output modes of the refinery, which are probability boosted to near deterministic operation multiplied by that clock speed. But the per mode, per channel rate is, 1 per microsecond.
I see. That's impressive. Thanks.
Any other question? Okay. Yes, we have a question.
Hi, thank you very much. Very interesting talk. The question about currently how many GKP qubits can be generated? What is the size of the GKP, cluster state you can generate in the system?
Yeah, so in Aurora, 12, you think of it as 12 physical qubits. Now, we've built systems that have many more modes. Borealis had 216 entangled modes in a three-dimensional entangled state. I wouldn't exactly call it a cluster state because the entangling weights were a little different for that application, but it could be a cluster state if you just reprogrammed it as such. So we've gone up to 216, but those are squeeze states. Those are entangled squeeze states and not entangled GKP states. So the short answer to your question is 12.
Thank you very much.
Have you checked the entanglement between the GKP qubits?
Interesting question. I think in Aurora that certainly exists. It would be pretty noisy signature, but you can certainly see correlations. I don't know if I go so far as to say that the entanglement has been shown, but certainly there would be correlations. In Aurora, you can definitely see the entanglement in the bell pairs when they're made of squeeze states. But because GKP qubits haven't been boosted to high enough probabilities and they're pretty low quality in Aurora, I don't know that you'd be able to actually look at entanglement metric for the GKP qubits in Aurora. Probably not.
Okay, sounds interesting. And look into that further details. Any other questions from the audience or online? So I have another question. So you mentioned you can generate GKP bell state and then cluster state. If my understanding is correct, so in the architecture, you also need to generate magic GKP state. So in terms of hardware, is it more difficult to make the magic state, or is more or less the same as the standard GKP state?
Yeah, it's a great question. So more or less the same is the short answer. The same types of circuits that generate GKP qubits can also be programmed to generate GKP magic states as opposed to GKP sensor states. There are subtleties in how you optimize them and how you do breeding, how you'll optimize the circuits for that. And it may make more sense to, again, do magic state distillation. But the short answer is there's not a big difference so far as we've seen in the qubit factory when it's the sectors of it dedicated to making magic states versus the sectors of it dedicated to making sensor states.
I see. Great. Okay, is there any other questions? If not, let's thank the speaker again. It's a great talk.
Thanks very much for everyone's great questions and for all your attention.
Rogerio, you have a follow-up question? Oh, no, it's just clapping. Yeah.
I'm just clapping my hand. Thank you, Zach. It was amazing.
Thank you, Zach.
Thanks, great talk.
So thank you to be giving a talk with us today. We will send you a souvenir soon.
Appreciate it.
Yeah.
Have a great day, everyone. Take care.
Yeah.